Hello, welcome back. As you can tell from the resolution, the operational words for our class online from here on are semi-pro. I'm trying to get a better resolution camera going, um, but for the time being, yes, this is my basement. um, So, originally, I was planning to use the university's boilercast system, which presumably has a much better camera and a document camera at that. Um, but now the university and their ever evolving response to this pandemic has decided that they are more or less shutting the campus down, meaning that I cannot go into the classroom. So, I am going to do my best to communicate with you guys by posting notes for lectures and by recording these lectures here on the YouTube channel. And hopefully, between those two things and your ability to communicate via email and via this piazza, we will get through this together. So, I imagine you have all kinds of questions, like how's your Clash of Clans village doing, Professor? Very well, thank you. Managing 10-year-olds is a little bit of a chore, but if anyone tells you that, defeating children at a children's game isn't satisfying, they're wrong. What else? How are you doing, Professor? Well, great. Great. I've got a bunker here. I've got a chalkboard. Look at that. Which we'll be using momentarily. I've got a giant freezer full of food. And I've got all the basic trappings of pandemic response. So here, Lysol spray. I had to roll some septuagenarian and pay less to get it, but I got it. And here, useful but in a different sense, my AC/DC lighter from the early 1990s. And together, serious defense against zombies. So we're well equipped here. Oh yeah, look at that. Tons of toilet paper. This is just the tip of the iceberg, believe me. No, I'm not selling it online. And a freezer full of food. Yeah. So we're good here. I hope you guys are doing well. If you're not, well, I was looking for real estate in your area anyway. I have one half piece of chalk. I have to go in and brave the zombie hordes at the university today and retrieve my chalk from the office. But for the time being, we have one piece of chalk. And today's topic, so I just want to remind you where we were before all this happened. So we had finished section 3.5, and that was on the Cauchy criterion. And I'm hoping that's legible. And if it is not legible, if legibility is a serious issue, again, I apologize. This is the first day. I'm going to try and get a better resolution camera and a better setup. But I'm doing my best. And again, I will post the notes online. So try not to panic. So the Cauchy criterion, section 3.5, we have done. And then section 3.6. That's on something called proper divergence. Okay, so maybe I can move this a little closer. See if we can't zoom in a little. Okay? So proper divergence. And proper divergence is actually something that we covered earlier in the course when we were discussing the notion of when a sequence has a limit. Okay, so all that proper divergence means is that a sequence has limit plus or minus infinity. So in general, we say that a sequence diverges if it does not have a limit. If the limit as n goes to infinity of xn does not exist. However, failing to exist could mean that it goes to plus or minus infinity, and that is somehow a special sort of divergence, one that we want to single out. So I will write that down. Xn is properly divergent if the limit as n goes to infinity of xn is equal to plus or minus infinity. Okay? So one of those two situations. Alrighty. So that covers all, really, of 3.5 and 3.6, since we've already really covered 3.6 earlier. So the other thing that I am going to take from the university, shamelessly, is a full-sized eraser, since I'm currently just working with this little thing. Alright, so that brings us to section 3.7, which is on infinite series. Okay, so infinite series has to do with the idea of possibly taking a sequence of numbers and adding them all up and asking whether that makes any sense at all. Does it make sense to take a sequence xn and start adding x1 plus x2 plus x3 plus x4? And does it make sense to ask if that has some meaning? Okay? And it turns out that it does make sense to ask that, and indeed we can develop a whole theory around that. Okay? So, let's start by saying let xn be a sequence. The series generated by xn is the... So a series is itself a sequence, is the sequence. It's a new sequence generated from the original sequence by looking at the sequence of what are called partial sums. The sequence S sub k, which is the sum from n equals 1 up to k of xn, which is shorthand for the sum of the first k terms. Jeepers. Alright, if the video cut out there, I'm really sorry. I guess I will have to agitate the machine every now and again. Okay, so to recap, let xn be a sequence. This series is a new sequence generated by xn, and the way in which this new sequence is generated is just by looking at these so-called partial sums. That is, S sub k is the sum of x1, x2, and so on up through xk. So this is something you can always define. Given a sequence, you can define the sequence of partial sums. Okay? So that is the series. It's the sequence of partial sums. All right? And then the big question when you have a series is whether or not it converges. And so at the end of the day, that's just the question of whether a certain sequence converges. Nothing new there, but the tools and the techniques and the intuition used to figure out whether or not a given series converges are specific and somewhat different, perhaps, than what we use for sequences in general. Okay, so the series for xn converges if that sequence of partial sums that I just defined, and then of course had to erase, if that sequence of partial sums converges. Otherwise, the series diverges. Okay, straightforward enough. If it converges, then we write that the sum from n equals 1 to infinity of xn is equal to L. Okay? So here L is the number to which this series, the sequence of partial sums, converges. And so this is our notation, our shorthand for that statement. Okay? We write sort of glibly that the sum from n equals 1 to infinity of xn is equal to L. Right? And this is the meaning of that statement unpacked. All right. Where did my... There it is. One thing that happens fairly frequently when studying series is that you may consider a series generated by a sequence, but not necessarily starting from x1. Okay, you might start from x0. This will be the case in the geometric series, as we shall see. But you could start from x5 and so on. So let me just make note of the notation for that, so we can we can start a series from any point So, for example, e.g., we could consider the sum from, say, n equals 5 to infinity of xn, so what happens here? Well, this is still a series. It's still generated in some sense by xn, but the partial sums are going to be different, where s sub k is going to be equal to the sum from n equals 5 up to k of x n. Okay? And what I would like to point out here is that now s sub k has changed. Okay? Right? So previously, in the case of the usual series generated by this sequence xn, we would have s sub k, say s sub 5, would be the sum of x1, x2, x3, x4, and x5. Whereas now, s sub 5, well, it tells me here I'm supposed to start at n equals 5. So in fact, s sub 5 now is just the term x5. Okay, so the definition of these SKs has changed. It will nevertheless turn out to be the case, and is in fact straightforward to see, ultimately, that this series, starting from some different number, in this case 5, but could be any different number in there, will converge if and only if the original series converges. Okay, so the question of convergence doesn't change, but what exactly the new series converges to may change depending on where you start the series. Ooh. I mean, teaching from home has some advantages. You have to make your own coffee. Oh. Although, since I'm in the basement, there's still no light, but whatever. We were accustomed to that. Okay, so that's the basic definition of what an infinite series is. Okay, and the partial sums. So let's now consider some examples. Actually, it's our first day back. And for those of you that are wondering, yes, we have reached the CDC crisis level where you are supposed to actually wash your legs in the shower instead of just letting the shampoo run down over your legs and calling it good. Okay? That is among the recommended techniques for defeating the coronavirus. Wash your hands. Don't go outside. Seriously, don't go outside. Okay? Don't go outside. But, you know, now there are even fewer rules than there were before, so maybe we can go on tour. Let's go on tour. Right. Check for boogers. Yeah, no boogers. Good. All right, so this is my basement. So there we can see up there in the corner that weird wooden thing. That's the It's part of the climbing training center. You see, because now I'm stuck in the basement for whatever months, but I plan to emerge like a phoenix, crushing pool balls into dust with my bare hands. And yes, that's my Christmas tree. Over here, we have the deep freeze. All kinds of delicious goodies. I'm good here in the bunker for like 2 months. And altogether too much pasta. That's about like a, let's see. With my kids, that's probably about a 4-day supply of cereal and pasta right there. And what else? It's not a very exciting basement, I must admit. But anyway, we needed some kind of diversion. I have to admit, not doing this, live is depressing. I'm sure it is for you too. But we're gonna make it. We're gonna make it. All right, let me make sure that zoom in here. That's what we call physical zoom, right there. Alrighty, so let's have some examples of series. So maybe the best known one is the following. So we consider, and already this is an example where we are not actually going to start the partial sums of the series from n equals 1. In fact, we're going to start them from n equals 0 up to infinity. Okay? And the terms of the sequence are going to be of the form r to the n, where r, of course, is just some real number. Okay? And then let's write down what the partial sum is. So S sub k, that's going to be, well, we're going to start with r to the power of 0, which is just 1 plus r squared, and we will keep going all the way out to r to the k. Okay? And it turns out that there is a fairly nice algebraic formula which will allow you to write the sum of these first k terms, the partial sum s to the k, more compactly. Okay, so let's write that down. So this should be equal to, I claim, let's see, what will it be? It should be 1 minus r to the k plus 1 all over 1 minus r. I claim. Why should that be the case? Well, it should be something that's relatively straightforward to check, and the way to check this claim is to take, so really we have two sides of the equation here. On the one side we have this partial sum written as a partial sum. On the other side we have this closed form here, okay? So those two things should be equal, so what I'm going to do is multiply both sides of that equation by this 1 minus r. In other words, this claim will be true if and only if 1 minus r times 1 plus r plus all the way up to r to the k is in fact equal to 1 minus r to the k plus 1. Okay? That's what we would like to be true. So I'm going to erase that board and then rewrite that last line at the top and just check to make sure that I'm not lying. Okay, so once again, I had the claim that 1 minus r times 1 plus r squared, and so on, all the way up to r to the k, was going to be equal to 1 minus r to the k plus 1. And this calculation is an example of something called a telescoping sum. Okay, so first I'm going to take this entire expression here and multiply it by 1. So I'll get 1 plus r squared all the way up to r to the k. Then I'm going to take the whole thing and multiply it by minus r and add it to this. And I'm going to do that, and I'm going to write minus r times this whole thing just below this and shift it over a little bit so we can see how things cancel out. So minus r times 1 will give me minus r. Minus r times r will give me minus r squared. You can probably see where this is going. We'll get minus r to the k. And then finally, off on its own, with nothing to pair with, will be minus r to the k plus 1. And then we'll see that these guys all cancel out. And so, indeed, we wind up with 1 minus r to the k plus 1. Okay, so once again, the purpose of doing all of that was to notice that the partial sum s sub k, which is by definition the sum from n equals 0 up to k of r to the n, can be expressed as 1 minus r to the k plus 1 all over 1 minus r. Okay? So this is what the sequence of partial sums looks like, right? And remember, the series then will converge if and only if this sequence of partial sums converges. So we would like this guy to converge. All right? Now, what we're going to see down the road, maybe in this lecture, maybe in the next, is that you can definitely show, there is a very good reason why this series with k replaced with infinity does not converge, or where these partial sums do not converge if the absolute value of r is greater than or equal to 1. However, if the absolute value of r is strictly less than 1, then as k gets very large, this term here, the r to the k plus 1 term, that vanishes, okay? And we're going to get convergence. So let me write that on the next board. Okay, so we have that the partial sum s sub k is equal to 1 minus r to the k plus 1, all divided by 1 minus r, okay? And then if the absolute value of r is less than 1, r to the k plus 1 converges to 0. We're not going to provide the full proof for that. However, on the test or exam at this point, that is definitely a legitimate question that I would expect you to be able to write down the details for. Okay? So in this case, what happens? Well, that means that as k goes to infinity, this term up here, this r to the k plus 1, goes to 0, and so the whole thing converges to 1 over 1 minus r. Okay? Which then finally, I guess, we could write as the sum from n equals 0 to infinity of r to the n. That's the formula for the geometric series in the case that the absolute value of r is strictly less than 1, and that's the best you can do. We will see later on that if the absolute value of r is greater than or equal to 1, then the series diverges. Okay. Man, you should have seen the emails that I got coming in from the university. I mean, it was like, day one was like, make sure you wash your hands. And then day 2 was like, we're gonna move to online classes. And then, and then day 3 was, members of the community have been pre-selected to leave Earth and save humanity, and you are not among them. So I have no idea what tomorrow's email is going to be. Earth canceled or something like that. My retirement fund is like now, I think it's like $4.76, something like that. But fortunately, I've got another 30 years, hopefully, to recover from this. And, if things don't go so well, there's going to be a whole lot of job opportunities for everybody. That's grim. Sorry. Okay, so that's example 1 of a series. Let's have another. So let's consider the sum from n equals 1 to infinity of minus 1 to the n. Okay? So regardless of whether or not a given series converges, you can still write down this expression. It's just that it may converge and it may not converge. It may have meaning and be equal to some real number, or it may have no meaning whatsoever. But you're free to write it down. Okay? So the question then is, does this converge? Okay, and we know what it means for a series to converge. It means that the sequence of partial sums has to converge. So we consider S sub k, which is the sum from n equals 1 up to k of minus 1 to the n. And let's write down a few terms here, okay? So then S sub 1, the very first partial sum, I guess that's just going to be minus 1 to the 1. So it'll be minus 1. S2 is going to be the first 2 terms in the series. And so that's going to be minus 1 plus 1. which is 0. And then S3 is going to be minus 1 plus 1 minus 1, which is minus 1. And so on. And there's a very straightforward pattern developing here. The partial sum is going to be minus 1 if the index is odd, and it's going to be 0 if the index is even. So let's encapsulate that over here. So S sub k is equal to minus 1 k odd and 0 when k is even. Okay? In particular, evidently, the sequence of partial sums does not converge. It just flips back and forth, alternates between 0 and minus 1, and therefore this infinite series diverges. Okay? So this diverges. So we've had one convergent example, one divergent example. Let's have one more convergent example here. You know, based on the feedback I'm getting, this is going really well. I could get used to this. Okay. Let's see. Let's try this guy here. So let's consider the series, the sum from n equals 1 to infinity of 1 over n times n plus 1. Okay? Now, what we're going to see later on, and what we're going to get used to in general, is that there are certain flavors, if you like, of sequences that will generally produce a convergent series. Okay? The flavor, roughly, of the sequence generating this series is that it looks something like 1 over n squared, right? It's not exactly n squared. The denominator is n squared plus n. But the denominator is a polynomial and it's quadratic, okay? What we're going to see is that whenever you have a sequence, a generating sequence that's of the form 1 over, roughly speaking, n to some power where the power is bigger than 1, then that series is going to converge. Basically what's happening is that the terms in the generating sequence, these, in this case, 1 over n times n plus 1 terms, they're going to 0 fast enough that even when you start adding them all up, you are still going to get this whole thing, the partial sums, converging to some number. Okay? So that's a general ethos, because if you are faced with a question which says, okay, here is a series, does it converge or not? I mean, the first thing that you want is some kind of guess, some sort of toolkit of generic sequences which generate series that do in fact converge. And so what I'm trying to tell you here is that basically your guess for this one would be that yes, this series converges, and the reason for that guess would be that it roughly has the form 1 over our index squared. Okay? That does not necessarily give you a direct route to proving that it's convergent, but it at least gives you the right answer, which is a start. Okay. So, of course, we're going to have to work with the partial sums, and then the key observation here is basically just trickery, right? And oftentimes, when trying to figure out how to prove that a given series converges, you need something, some sort of insight. Okay, so the thing we're going to note here is that if you look at a generic algebraic expression of the form 1 over k times k plus 1, then you can rewrite this as 1 over k, minus 1 over k plus 1. Okay? It's just algebra. I will leave that to you. But this one clever observation is enough to get us to the finish line for this series. Okay? So note then that S sub k is equal to, well, it's, I guess you could write it as 1 over 1 times 2 plus 1 over 2 times 3 plus, and you would keep going all the way up to 1 over k times k plus 1. Now, each one of these terms here has the form 1 over k, k plus 1, for differing k's, of course. And so what we're going to do is apply this little algebraic equality to each one of these terms. Try and squeeze it in here. So we're going to get that this guy then will be the same as 1 over 1 minus 1 half. The second term is going to be 1 half minus 1 third, and so on, all the way out to 1 over k minus 1 over k plus 1. And what's going to happen is that you are going to get a telescoping effect. So you can see here, in the first term here, I've split it up now as 1 over 1 minus 1 half. In the second term, I've split it up as 1 half minus 1 third. The minus 1 half from the first term cancels with the positive 1 half from the second term. Similarly, the minus 1 third from the second term will cancel with a positive 1 third. This guy will be 1 third minus 1 quarter. The minus 1 third from this term will cancel with the plus 1 third from this term, and so on. Essentially, everything will cancel out except for the 1 over 1 term at the very beginning and the minus 1 over k plus 1 term at the very end. Okay, so all that's going to survive after you've made this observation here is that S sub k, this partial sum, is just going to be equal to 1 minus 1 over k plus 1. Okay, so let's write that down. Next, I'm actually just going to leave that series up there and erase this calculation. Okay, so then finally what we're going to get is that S sub k is equal to 1 minus 1 over k plus 1, which clearly converges to 1 as k goes to infinity, and therefore this guy converges, and converges to 1, in fact. Okay, so there's another example of a convergent series. And so let me finish off this lecture with an important fact. It's very useful because it allows you to rule out convergence for a great many series. Okay? So it's the following little theorem. It says if your series converges, then it must be the case that the xn's converge to 0. Okay? The way the definition of convergence for a series is set up forces a convergent series to have the xn's going to 0. So, again, this is very useful because you can immediately look at most examples of series that you're given and check, at the very least, whether or not the xn's are going to 0. If they're not going to 0, you're done. That series diverges. If they do go to 0, well, you're not done yet. That doesn't necessarily mean it converges, but you haven't ruled it out. Okay, so I'll finish off with this proof. So it's fairly straightforward. We just note that, I guess, you can compute x sub k, element of the original sequence, as a difference of two consecutive partial sums. If you take the kth partial sum and you subtract the k minus first partial sum, all that survives is x sub k. Then all you have to do is take the limit of both sides. Okay? So, I guess we could note also s sub k converges to some L. Right? That's our basic assumption, that the series converges. And another way to say that, or in fact the definition of that statement, is that the sequence of partial sums converges to some number L. Okay? Thus, the limit of the xk's is the limit of sk minus sk minus 1, right? And both of these two sequences converge to the same thing. That's L minus L, which is 0. Okay, so that tells you that the limit of the xk's is 0. All right, and that's about all the time we have for one lecture. I'd ask if there are any questions, but, well, you know, this is one of the unfortunate features of where we are right now. So I did set up this Piazza thing for our class. You can use that to ask questions. I'm probably better with email, but one way or another, there should be latitude for you to ask questions. And of course, I'm going to enjoy the sort of blissful 15 minutes between now when I shut this off and when I throw up my hands in frustration at trying to upload this and find that, I don't know, all the text is mirrored or nothing works. Yeah, and so if there are any problems or gentle suggestions or what have you, feel free to let me know via email. And hopefully this will all pan out for us. Oh, incidentally, I do still plan. So, assignments. Crap. Should have done this at the beginning. I put a test assignment on Blackboard. Okay, so we are set up to use something called GradeScope. So if you log into your Blackboard, there should be a link for Gradescope there, and you should see a test assignment. This is worth 5 free points if you just submit it, so that I know you're enrolled, that you're using Gradescope, that it's working properly for everybody, okay? And then on Wednesday, provided everything goes smoothly with that first test assignment, I will give you a new assignment. The assignments will then be due as they were before. Once a week, you will have to submit a PDF file through Gradescope, and the TA will grade them through Gradescope. Yeah, but we will get to that in more detail on Wednesday after the test assignment hopefully comes through. All right, stay safe, wash your hands. Bye.